So we're starting a chapter on evolution, and it spans a lot of information that kind of jumps around, so these videos will seem a little bit hodgepodgey with information because it doesn't have a complete consistency, but a lot of it's vocabulary, as you can see in this first part with biogenesis. Bio meaning life and genesis meaning creation or start. Not necessarily a process or concept that describes the start of life, but it's more that it states that life gives rise to life, or living things are going to give rise to other living things. And if you recall the cell theory, we had heard something along the same semantics where it said cells come from pre-existing cells. So think of it like that. That's the current understanding. But prior to that, people did believe in spontaneous generation, where life can arise from non-living things. And this was all just completely based on observation, just like you make observations. You know, they saw things such as mice that would come out from haystacks and thinking that the mice potentially came from that haystack, which they know is non-living. So they had some science experiments that disproved this process. The first being reedy, and here's a picture of that. Inside of these vials, there are slabs of beef, which is obviously a non-living specimen at this point. And these things surrounding it are flies. And people had seen that maggots came out of this beef at one point and thought that the beef actually was giving rise to these maggots. So that's where the life from non-living came from. But this guy was set out to prove that this is not possible. So he takes this slab of beef, puts it into a closed container so that the flies cannot actually touch the beef. And over here we have a kind of before and after. Here are the maggots. I don't know why they kind of drew at this point. I wish that they would have just shown that this vial has just flies around. But what would happen is, since it's open, the flies can touch the meat, and then they can lay their eggs, which is the next generation of flies, since they don't give birth the way that humans do. Then what will happen is the only flies that had access to the beef is where the maggots would form. So what he said is, I just disproved the idea of spontaneous generation, because this vial, if spontaneous generation were capable of happening, would still produce maggots. But I prevented them from forming. So he disproved spontaneous generation of larger or macro organisms. People are still in the understanding that maybe smaller organisms can potentially go through spontaneous generation. So here we have another experiment. Last name is Spallanzani. And Spallanzani, what he did is he was trying to do stuff with microorganisms or microbials. And broth is more of an environment where microbes can live. It's, you know, different variations, but here we have a broth. It's a somewhat soupy material. So we heated it in both scenarios. Think of this as our one group, and here is our other group, and we're kind of going left to right. He heated both of them because heating is going to kill anything that began, and therefore he would start with all non-living stuff. One of them he cooled and left the flask open. He waited, and there was growth in there. So he wasn't shocked because he was trying to disprove spontaneous generation at the microbial level. Down here he put a flask on, cooled it, but put a stopper on it and prevented any entrance of previous microbes from getting. He waited, no growth. Opened the flask, and there and behold, a few days later, I'm sure growth happened. So he felt he disproved spontaneous generation. Sorry, I'm going to have some typos as I'm doing this live. Spontaneous generation of microbes or smaller organisms. People had some issues with this. They said, they came up with reasons, as you are trying to still potentially think of the idea. Someone's trying to change your mind, but you didn't really want to change your mind. So he came up with potential problems, and people said that what he had done is heated the broth a little too much, and they had this belief that there was this thing called vital force, and I don't know if that's really an official term or just how textbooks describe it. But these people said that there was this vital force, and the heat, I don't know if killed is the best word, but the heat killed or prevented the formation of this vital force. And when you stoppered the flask up here, you prevented the vital force from getting in. So they said, of course, microbes won't grow because it's not that you prevented microbes from getting in, you prevented this vital force from entering. So his experiment, albeit actually probably something that could have proven spontaneous generation as not being possible, people were still not satisfied with his experimental design, which that's their prerogative. So Pasteur came up with an alternative that kind of took their issues into his experimental design. He boiled the process And instead of stopping it, he created this special flask, this S-shaped flask, which apparently has the ability to stop microbes from entering and getting through this long neck, but it is open. So people that had this idea that there was this intangible force that was unable to reach that, he said it's open. It can get there. So at this point, this experiment did and is given credit for disproving spontaneous generation. At the microbe level. So there we have it. 3 experiments disproving spontaneous generation, agreeing with biogenesis. So we get into the fossils, again, switching gears. And so a fossil is evidence. You know what? I'm going to change the font here. I feel like I'm sure you've been a little bit annoyed as let's change this font to normal. I apologize it took so long. All right. So the fossil record. This is evidence. Oh, great. All right, let's try that one more time. Change. Evidence to the existence of an organism. Evidence to the existence of an organism that was once there, is no longer there, but they left some type of track behind. There are different types. Types of fossils include trace, imprint, mold, cast, petrified, and amber. So what I'm going to do is I'm going to show you a little clip of a PowerPoint that walks us through this. Here you have trace fossils. I kind of put some pictures here to familiarize ourselves with 2 examples. Here we have a bike track trail, and here we have a snow trail. And a trace fossil is a fossil where you can identify that something or someone has been present, but it's not forever. When people think of a fossil, they often think of dinosaurs and the bones that they leave behind. That's their example of a fossil, but there are many types. So here's a trace fossil, and what it did is it shows for a little bit of time, you can obviously see this, but then eventually it might go away. The next one, this is an imprint fossil. And so an imprint fossil kind of is a shallow impression. That's how I somewhat differentiate it. And it's in rock. Oftentimes sedimentary rock is your best formation for fossils, given that they formed based on sediments coming together. They look like somewhat a photograph. So here in this fish, it doesn't even look like the fish was there. It just looks like it kind of splatted against it, and that was it. That's how I kind of differentiate an imprint from the next one, which is a mold. And so mold, you can see there's a much deeper impression on this and over here. So to differentiate between these two, it's a fine line, I'm sure. And, you know, we're not going to argue over it. But if I were to give you a third, like a quiz on this or pictures, I definitely would be more extreme with it as opposed to walking that fine line of what's an imprint versus a mold. This, you can see these pictures very shallow. The mold are much deeper. You can actually see how deep it goes in there. So here are 2 examples. Another example, anything like a foot in concrete, that might be an example of a mold. So the next one is a cast. And so a cast and mold actually go together. So I'm going to flip back and forth. In order to create a cast, you need a mold there at first. So you may have heard of a jello mold, and a jello mold is a plastic indentation. So you fill the jello in liquid form, and then eventually it cools and it hardens and it will form a shape. The shape that it forms is actually what's known as a cast. So this organism right here is a rock formation. So a mold was produced from that organism originally. And what happened over time, more sediments or rocks filled in, and now were removed, and you can see this is an exact replica. So cast fossils kind of are more three-dimensional, and they come out at you as opposed to molds that go inward. So this cast is a three-dimensional. It's basically a replica of the organism that made the mold, and that's how I'm going to kind of stop there. But that's the big thing. These two go hand in hand. You have to have the mold first, then you have the cast. The next one is petrified, and this looks like a tree trunk that has been sliced a few times, but this is a petrified fossil, as I Google searched it. The idea here is that it takes the shape of the object that it replaces. So these are all minerals and rocks that replace it, but it's been petrified. So petrified, in just the context of the word petrified, means turned to stone. Whether you know Greek mythology, whether you know Harry Potter, that word has been thrown around because petrified means turned to stone. So here we don't have to understand the process. It's just recognizing fossils at this level, and then next time you might learn about them, you might learn more about the process itself. And finally, we have amber. Amber is dried sap from trees, and inside, this is how you recognize, like Jurassic Park, that's the whole concept, is that within this there was an insect that might have been trapped, and it doesn't degrade because oxygen isn't present, and it basically is preserved. So you know that there is an organism there because you can see it, and this is amber. It's made into jewelry and things like that. So those are the 6 types of fossils, and what we do with fossils is help us determine ages of. The reason why it's in this chapter is we talk about evolution, how things have changed. So we can analyze, as an archaeologist would analyze fossil records. So I'm going to go through 2 ways in which we analyze fossils. So here we have the next thing. With fossils and determining ages of things, we use radioactive dating. Radioactive dating relies on the concept of radioactive isotopes, and from previous chapters, isotopes are 2 atoms that have a varying number of neutrons, so therefore they have a varying mass, but they're of the same atom, so they have the same number of protons. The radioactive isotope is unstable, so what will happen is the unstable isotope is going to emit radiation, which are different forms of radiation. In biology, we don't go through all the details of that, but in chemistry, you'll learn a lot more about that. The word decay means that what's happening is a radioactive isotope is transforming from the unstable version of itself to a stable variety. And there are different end results of that. We're not going through every example. Here's an example the textbook uses for the radioactive decay of potassium-40. So that means that it's potassium and it has an atomic mass of 40. There are other variations of potassium from the periodic table, but this is the radioactive version. So this chart talks about how at the beginning of the record of this sample that you would find that has this radioactive isotope within it, it's 100% of potassium-40, and what we notice is half-life. That's the idea that the amount of time it takes for half of the mass of that radioactive isotope to transition to stable form. So if we notice here at 1, where the fraction is 1/2, how much time went through? So that's the axis down here. So what that's saying is we've gone about 1.1 billion years. So if they had the ability to calculate, and they do this, we've not been around for 1.1 billion years as humans. So there are calculations to extrapolate. But what this says is that they have figured out that it would take 1.1 billion years for potassium-40 to decay, where half of it is still unstable of that original amount, but the other 50% is now in a stable form. So what we notice here is to get down to a quarter remaining, that means that this half has been cut down another time. It's going to take exactly another 1.1 billion years. So if this is 1.1, adding another 1.1 is roughly 2.2, so there we have it. So that's at half-life number 2. And then for it to go down to cut 1/4 again, so we're down to 1/8, that's going to take another 1.1 billion years. And this is approximation. You can kind of see it's not exactly on this line, so it must be a little bit more than 1.1 billion. But there are different half-lives for different radioactive isotopes. So these are some common ones. The most common one that you often see in books as well is carbon. So carbon-14, we're back to that font, I'm sorry. So carbon-14 has a half-life of roughly 5,730 years. So what will happen is every 5,730 years, the mass that is available in a sample for carbon-14 will degrade. So if you have a sample of 100 grams of C14, what that says is after one half-life, that means 5,730 years has passed, you should have 50 grams still remaining of carbon-14. The other 50 grams that was lost is now the stable form of that radioactive isotope, was actually a form of nitrogen. So it doesn't just necessarily transition from the radioactive form to the non-radioactive form of the same element. After another half-life, we would be down to 25 grams. After another half-life, we would be down to 12.5 grams. So if I have a sample that I knew originally started at 100 grams and finished at 12.5 grams, I would be able to say 1, 2, 3 half-lives have taken place, each half-life being 5,730 years. So whatever 5,730 times 3 would be the age of my sample at that point.